IoT has wide applications. For example, combining with AI models, the camera can be used in city security surveillance, monitoring the health of animals, as well as transportation monitoring. The AI IoT devices need to be small in size for low power consumption and high inference speed. These small-sized models can be generated by an IoT company. Knowledge distillation is used to train a small model from a large model with presumed data. For instance, the company assumes that the smart cameras are used to recognize dogs, chickens, and bicycles. The model generated during knowledge distillation in the manufacturing domain is deployed as the edge AI model in the customer domain. However, real-world data may differ significantly from the dataset used to train the original models, potentially including rare conditions or corner cases. This discrepancy can reduce inference accuracy. For example, an AIoT company may design a smart camera to detect common chicken breeds, but it may struggle with rare breeds unique to the customer's environment. In critical scenarios like intelligent traffic, such accuracy degradation can impact safety. Thus, improving the edge AI model's alignment with real-world data is crucial. We assume that some users have local computing power and can retrain the small model. Allowing the user to change the AI model locally may cause legal issues. We let the user make local training to learn the discrepancy between the pre-trained knowledge and the knowledge actually needed. This discrepancy will be reported to the manufacturer. The manufacturer will regenerate the student model and give it to the customer as long as the model passes the performance check. For example, the manufacturer does not want the AI model to lose its knowledge in bicycle recognition. The student models are using the knowledge distillation process from a relatively larger AI model, which we call the tutor model. The tutor model, in turn, may be derived for specific application scenarios from an even larger AI model, referred to as the teacher, which is managed by the AIoT company. The student is given to the customer as an edge AI model for IoT applications. In the customer domain, real-world data may differ from the presumed data, causing accuracy issues. Assuming the customer has certain computation power, two new tutor models are created using the reverse knowledge distillation process, where the small model takes the role of a teacher to train larger models. Tutor 1 is trained with the presumed dataset to mimic the edge AI model's performance. Tutor 2 is trained with both the presumed dataset and the customer's private data to reflect real-world conditions. The knowledge gap between these two tutors highlights differences between the presumed and real-world data. The difference in model weights between Tutor 1 and Tutor 2 is calculated. This weight difference is sent back to the manufacturer domain to update the original tutor model. This ensures no private data is shared, protecting customer privacy. The tutor model undergoes a new KD process to refine the edge AI model, improving its accuracy for real-world applications. The manufacturer verifies the updated tutor model to ensure it meets performance requirements before deployment. Using the tutor model, the edge AI model will be regenerated using the knowledge distillation process. The original edge AI model was trained using a presumed dataset that included data for several object categories, such as horses. This model initially performed well on those categories but lacked knowledge of new, unexpected categories like dogs, which appeared later in the customer's real-world scenario. In the reverse knowledge distillation, the presumed dataset in the customer domain was modified. The horse category was removed because the customer has no horses. The dog category was added as private data. This simulates a scenario where the customer's needs have shifted to a different IoT use case. Using the updated tutor model, a new edge AI model was generated via the knowledge distillation process. This updated model now includes knowledge of the dog category and reduced reliance on outdated horse data. We also compare the performance of the edge AI model trained using the KD process with that of direct local training. The model obtained through the DiReDi method outperforms the one trained directly on the local system.